Hello world! Right now, your computer is lying to every program running on it simultaneously. Your browser thinks it owns the CPU. Your music player thinks it owns the CPU. And even your text editor, for example VS Code, thinks that it owns CPU. But actually, none of them do. There's only one program that owns everything, decides who gets what and when. It's called the operating system. And today, we open it up. Your CPU has one job. It executes instructions, one at a time. Not two at a time, not 10, just one. Even on a modern processor with multiple cores, each core is doing exactly one thing at any given nanosecond. So how does your computer appear to run hundreds of programs at the same time? Your browser, your music, your terminal, your IDE. All of them simultaneously, without any of them knowing the others exist. The answer is it doesn't. Not really. What actually happens is so fast that it feels simultaneous. The operating system takes the CPU away from one program. It gives it to another. Takes it away again, gives it to another, thousands of times per second. So fast that every program believes it's the only one running. This is called scheduling. And the program that does it is the kernel, the core of operating system. The operating system isn't just one program. It's a layer. A layer between the code you write and the actual hardware underneath. Nothing touches the hardware directly. Everything goes through the OS, including ChatGPT, including your Python script. When you launch a program, the OS doesn't just run the code. It creates something called a process. A process is a running instance of a program, your code, plus its own chunk of memory, plus a unique ID number the OS uses to track it. That ID is called PID, process ID. Every process on your system has one. Your browser has one, your music player has one, even your terminal has one. And here's the key thing about processes. They don't know about each other. Your browser doesn't know your music player exists. Each process lives in its own isolated bubble of memory. If one crashes, the others keep running. That isolation is the OS's job. This is why modern computers don't crash entirely when one app dies. The process model is what makes that possible. Back to the CPU. It can only run one thing at a time. But you have dozens of processes. Someone has to decide who gets the CPU next, for how long, and in what order. That's the scheduler. The scheduler runs constantly. Every few milliseconds, it interrupts whatever is running, makes a decision, and hands the CPU to someone else. The slice of time each process gets is called a time slice, or quantum, typically around 1 seconds. 1 millisecond, that's 1,000th of a second. The scheduler is context switching between your programs faster than your eye can resolve. And every time it switches, it has to save the current program's entire state. All its registers, its program counter, everything. So it can resume exactly where it left off. This is called a context switch, and it happens thousands of times per second on your machine right now. Back inside our terminal, let's make this real. I want to show you every process running on this machine right now. Let's say PS, aux. The output is massive, hundreds of lines. Every row is a process. Every process has a PID, a unique ID number the OS uses to track it. Let me filter it down to something readable. Saying PS, aux, rep-e. Let's go ahead and say Python, Firefox, code, bash. Let's close it, say add -20. So there, these are the processes I care about for this video. VS Code, the terminal, any Python scripts running. Each one has its own PID, its own memory slice, its own CPU allocation. And critically, none of them know the others exist. Now, let me show you something that moves. This is top. Same information, but live. Updating every second. Let's try it by saying top. Watch the CPU column. These numbers are changing in real time. The OS is constantly making decisions. Who runs, who waits, who gets how much. And it does this thousands of times per second, while this screen updates once per second. The scheduler is the reason this is possible. Without it, one process would grab the CPU and never let go. So let me exit this, press Q to quit top. Last one, and this is the one I find most revealing. I'm going to run a simple command, ls, list the files in a directory, one of the most basic things a program can do. And I'm going to watch every single request it makes to the operating system while it does it. So let's say strace ls 2 bigger than and 1, say head -30. Look at this, ls, list files. That's all it does. And it's already made a dozen system calls before it even started listing. It's asking the OS for memory, checking which libraries to load, opening files. Every single step goes through the OS. There's no such thing as a program that talks directly to the hardware. Every program, no matter how simple, is in constant conversation with the operating system. And this is only the first 30 lines. ls makes hundreds of system calls total. Python scripts make thousands, and a web server millions per second. Here's the deepest idea in this video. Your program, any program, cannot directly touch the hardware. It cannot directly write to disk. It cannot directly send a network packet. It cannot directly access another process's memory. Everything has to go through the OS. When your program needs to do something that requires hardware, It makes a system call. It knocks on the OS's door and says, I need to read this file. I need to open a network connection. I need more memory. The OS checks if you're allowed, does the work, and returns the result. Everything your Python script does, printing to terminal, reading a file, connecting to the internet. Every single one of those actions is a system call underneath. Python calls the OS. The OS calls the hardware. The hardware responds. Python gets the result. This is why the OS is the most powerful piece of software on your machine. Not because it's the most complex, because everything runs through it. Everything. CPU, memory, operating systems. 3 layers, 3 videos. We started at the transistor. We're now at the layer that runs your code. Next video, we go up one more floor. Compilers. How the English you write turns into the electricity we talked about in episode 3. I'm X1000, logic behind the code. Signing out.